Hello everyone. My name is Dr. Abhijit Shah. I'm taking BTech chemistry course. This lecture is based on thermodynamics. Thermodynamics is a part of your BTech chemistry syllabus under module 2. So in this lecture, I'll discuss first law, second law, zeroth law, and of thermodynamics, third law of thermodynamics. We'll discuss different type of system. We'll discuss different type of boundary wall. We'll discuss uh, different type of energy like internal energy, enthalpy, Gibbs free energy, Helmholtz free energy, and also most importantly we'll discuss entropy in this lecture. So please listen this lecture carefully. It will helpful in your BTech chemistry. So first one, what is thermodynamics? Thermodynamics is a branch of science which deals with energy interaction and its effect with system and surroundings. Okay. Thermodynamics, there is two words. One is thermo and dynamics. Thermo means you can say heat, and dynamics means flow. So we can study the flow of heat in this part of in thermodynamics chapter. We generally discuss the flow of heat. The analysis of thermal system is achieved through the application of the conversion equation, namely conservation of mass, conservation of energy. Okay. Thermodynamics can be defined as a study of energy, that is energy transformation and its relation to matter. In thermodynamics, first we have to define a system and surroundings and the boundary wall. So what is system? System is the portion of the universe that we have selected for investigation. If we select some portion of our universe, that is called system. And the portion outside of the system is called the surroundings. Okay, so everything outside of the system is called surroundings. Now between system and surroundings there is a called boundary wall. Boundary wall is the real or imaginary surface that separate the system from its surroundings. It's called boundary wall. For example, if we have water in a beaker, so the water present, and if you want to study the water present inside is called system. Outside of the beaker is the surroundings, and this glass, which is separating surroundings and system, is called boundary wall. Now, depending on the boundary wall, system can be different type. One is called open system. Open system means the mass and energy can be transferred through the boundary wall. So mass and energy can be transferred through the boundary wall. With means exchange of mass and energy with surroundings is possible in open system. Closed system. Closed system means energy exchange. Means energy can be exchanged with surroundings, but no mass. For example, if we have a water bottle in fridge, right? Now if we take it out, okay, so what will happen? Slowly it will become heated. Water will come to room temperature. Why it's not coming? Because the energy outside is entering into the bottle, but there is no exchange in mass. Right? So this is an example of a closed system. Another one is isolated system, when the boundary wall is not allowing the exchange of both energy and matter. That is called isolated system. In isolated system, we are using that adiabatic boundary wall, which not allow the exchange of heat as well as matter. Next is the properties of system. System has some properties. Properties means mass of a system, volume of a system, temperature of system. They are called the properties, because we can define the system by defining the mass of a system. We can define the system by defining the volume and temperature pressure of the system. Right? So these are called the properties of the system. Now these properties of the system can be divided into two types. One is extensive property, another one intensive property. Extensive properties means the properties are independent of quantity or mass of a system. For example, temperature, pressure, density. They are independent of quantity or mass of a system. Extensive property. Extensive properties means the properties depends on the mass of a system. For example, volume of a system, energy present in the system, mass of a system. They are called extensive properties. Okay. So extensive properties per unit mass is called specific properties, and specific properties are intensive properties. So extensive properties per unit mass is the intensive property. Okay. Next one is the process. Okay, so what is process? So if a system undergoes a change, that is called process. Now process has some path. Means, for example, system is initially present in state 1. With time, it going to state 2. Now it can go by two paths. One is path A, another is path B. Right? So what process is the change of state 1 to state 2 is called process. And path means the change follows some way, some path. That is the path. Okay. Now, process can be two types. One is reversible process, another is irreversible process. In reversible process, the change of the system is allowed to happen slowly in minute quantity. In an ideal reversible process, the change must occur in a successive stage of infinitesimal quantities. A reversible process must be such that the system change back to its initial condition along the same path. The magnitude of change of thermodynamic quantities in different stages will be the same in the forward and backward direction, but with opposite in sign. Reversible process. Reversible process means the process occurs suddenly, spontaneously, without restriction of occurring in successive stage of infinitesimal quantities. Next one, type of chemical reaction. Chemical reactions can be different type, like exothermic reaction, endothermic reaction. Exothermic reaction means heat is liberated to the surroundings. Endothermic reaction means heat is absorbed from surroundings. Now chemical reaction can be different type, like based on process it can be different type. Isochoric process, isobaric process, isothermal process, and adiabatic process. Isochoric process means the process where there is no change in volume. Temperature, pressure will change, but no change in volume is called isochoric process. Isobaric process means the process where there is no change in pressure. Temperature and volume will change, but pressure will not change. Isothermal process means no change in temperature. Okay. No change in temperature. Here, pressure and volume will change, but temperature will remain same. An adiabatic process means no change in the heat. Q defines the heat, T defines temperature, P defines pressure, and V defines volume. So you can see this example of an isochoric process. So isochoric process, I told the volume will not change. So if we change, so with time, if we the volume will be, isochoric process means volume will not change. Isobaric process means pressure will not change. You are changing volume, but pressure is not changing. And isothermal process means temperature will not change. And this is the graph of pressure versus volume of an isothermal process. Next is the zeroth law of thermodynamics. Zeroth law of thermodynamics actually conservation of energy, right? Conservation of energy law. We have a conservation of energy law. So zeroth law of thermodynamics is similar like that. So it telling if two bodies are in thermal equilibrium with a third body separately, they are also thermal equilibrium with each other. Say system A and system B, if they are thermal equilibrium separately with system C, then A, B will be also in thermal equilibrium. Again, if system A is equilibrium with C and system B is thermal equilibrium with C, means system A and B is also in a thermal equilibrium. So this is called zeroth law of thermodynamics. Next one, mechanical work. How we can calculate the mechanical work? Work means force into distance. So force into distance, if we integrate, we'll get the mechanical work. Now force means pressure by area. So pressure by area. Now if we add this pressure by area here, so we'll get pressure into volume change to get, right? So if we know the pressure and corresponding volume change, we can calculate the work. Next is what is internal energy. Internal energy of the system, U, is the total of all kind of energy possessed by the particles that make up the system. So in our system there are many particles. So all energy, all kind of energy possessed by the particle that make up the system is the internal energy. Internal energy is an extensive property. Obviously, it is a mass dependent and it is a state function. Say if we have a system, if we apply some heat, means it will, we are increasing the internal energy of the system. So if we have a system, if we decreasing the heat, if we take out some heat from the system, means we are decreasing the internal energy of the system. Next one, first law of thermodynamics. So first law of thermodynamics, in all cases in which work is produced by a agency of heat or quantity of heat is consumed, means when a system consumes some heat, it produces some work. So there is some relation between this heat and work. The relation is dq, the amount of the heat if we apply it to a system. So it will increase the internal energy of the system plus it will produce some work. So this relation dq equal to du plus dw is called the first law of thermodynamics. So energy cannot be created or cannot be destroyed. So total energy of the universe will be constant. So energy can be converted from one form to another form. So from first law of thermodynamics, we can is an example of that conservation of energy. So whatever the heat we are applying to the system, it is converted into two forms. One, it is producing some work and it is giving some increase in the internal energy. Now they do one problem. See, gas is expanding against constant pressure up to atmosphere from 10 to 20 liter, absorb 30 calorie of heat. What is the change of the internal energy? So first we have to calculate the work. So here it is telling at constant pressure, so P is given, volume change is defined, that is 20 minus 10, it will be 10 volume change. So 10 into 2, so 20 is the work done. Okay, now we can calculate, means 1 liter atmosphere is equal to 24.21 calorie. So we can calculate it into calorie. Now from first law we know dq equal to du plus dw. Now dw value is 484. Dq value already given 300 calorie. So we can easily calculate du value. So this is the way we can solve the mathematical problem from first law of thermodynamics. Next topic is enthalpy. So total kinetic energy and potential energy of a system at constant pressure. Okay, enthalpy, enthalpy is also one type of energy. Now, if we take a work, if we take internal energy plus PV amount of work, right, that is called the internal energy. Enthalpy is the total energy of the system. Means if we apply some heat, that heat will increase the internal energy of the system. At the same time, it will perform some work. If the amount of the work is PV, so PV plus internal energy will get that enthalpy. So A is equal to U plus PV. Enthalpy is also an extensive property and it is a state function. Okay. If heat enter into the system, obviously U value will increase, so enthalpy will increase. If heat energy comes out from the system, U value will decrease and enthalpy will decrease. Next one, second law of thermodynamics. This law may be expressed in a varieties of equivalent ways. One is Clausius statement, Kelvin-Planck statement. What is Clausius statement? In second law of thermodynamics, Clausius statement is telling that It is not possible to construct a device that operates in a cycle and whose sole effect is to transfer heat from a cooler body to hotter body. Right? So heat cannot be transferred from cold body to hot body. That is Clausius statement. It is a in Clausius statement expressing second law of thermodynamics in this way. Kelvin Planck statement, it's telling it is impossible to take heat from hotter reservoir and convert it completely into work by a cyclic process without transferring a part of it to cooler reservoir. Same thing but different way. So what it is telling, it is impossible to take heat from hotter reservoir and convert it completely into work by a cyclic process without transferring a part of it to a cooler reservoir. It is not possible, right? So that is called Kelvin-Planck statement. So from second law of thermodynamics, we can get one diagram of heat engine. So in heat engine, there is a two sources of heat. One source of heat is higher in energy, another is lower in energy. So HT is indicating temperature, which is higher. HT is the temperature is cooler. So Q amount of is entering into the system and producing some work, and then some amount of the heat going to TC. Now we can calculate efficiency of a heat engine by this equation, that is TH minus TC divided by TH. Using that equation, we can calculate the efficiency of an heat engine. Next one, for what is spontaneous process? Spontaneous processes are those that can proceed without any outside intervention, right? For example, if we keep some body at a higher altitude, it will automatically flow to lower, right? But opposite one is not possible. So first one is spontaneous, second one is non-spontaneous. If we compress some gas molecule in a chamber, now if we open the chamber, all gas molecule diffuse. That is spontaneous, but opposite one non-spontaneous. So this is the example of a spontaneous process. So processes that are spontaneous in one direction, they are non-spontaneous in the reverse direction. Processes that are spontaneous at one temperature may be non-spontaneous in other temperature. Next is the entropy. Entropy is a property and it is also a state function. Entropy can be thought of an measure of randomness of a system. Means if a system, there are some particles, there are some gas molecule, how randomly it is moving, or how many number of particles are there. So randomness of a system is measured by entropy. It is an extensive property and it is also state function, and it is calculated by heat change in a reversible way divided by temperature. So this is the equation to calculate entropy change. So physical constant of entropy. Entropy can be viewed as a measure of molecular disorder or molecular randomness. As the system becomes more disordered, the position of the molecule becomes less predictable and entropy will increase. So if the material in a solid phase, the entropy will be low. If it is going to liquid phase, entropy will be high. If it is going to gaseous phase, entropy will be much more. So more disorderness is equivalent to increase in entropy. So there is some relation between entropy and spontaneity. When a system absorbs heat from surroundings or releases it to surroundings, both the system and surroundings undergoes a change in entropy. Right? When it is entering into system, so entropy of the system will increase. When it's entering into surroundings, entropy of surroundings will increase. So entropy of universe will be zero. For an irreversible process, entropy of the universe will be positive because a spontaneous process is possible when entropy increases. A spontaneous process is possible when entropy increases. If entropy is zero or negative, then the process will not be spontaneous. So many processes result in increasing in the system entropy. There are many processes. For example, increasing the volume that gas can occupy will increase the disorderness. So this is very common. If we increase the entropy, the process will be spontaneous. But there is some process where process is spontaneous but entropy decreases. For example, a chemical reaction between gas molecule that result a net decrease in the overall number of gas molecules. For example, this one, nitric oxide plus oxygen producing nitrogen dioxide. So initially there is the 3 number of molecules. After reaction there is 2 number of molecules. So we can see here entropy decreases because less number of molecules. Then why the reaction is spontaneous? So entropy. So from this example we can say entropy is not the only parameter to define whether a reaction will be spontaneous or not. There are some other things. Because of that we have to know the Gibbs free energy change. Okay, so next we have to discuss the Gibbs free energy after this. So regarding entropy, there is a law called third law of thermodynamics. It telling that entropy of a pure crystalline substance is zero at absolute zero temperature, means 0 Kelvin. So next one, entropy change of a chemical we can easily calculate. We have to take, if we know the chemical reaction, we have to calculate the entropy of product minus entropy of reactant. In that way, we can calculate the entropy change of a reaction. Okay. Next one, free energy. Since I told that entropy is not the only material to decide whether a reaction is spontaneous or not, so what is the another thing? Another thing is the free energy. So in free energy, Gibbs free energy is the most important parameter to check whether the reaction is spontaneous or not. In thermodynamics, there is two types of free energy. One is Gibbs free energy defined as an G. Another one, Helmholtz free energy defined as an A. So Gibbs free energy equation is G equal to H minus Ts. Means we know that H means enthalpy, T means temperature, and S means the entropy. So T into S indicating some amount of the heat, reversible heat change. So if we subtract the reversible heat change from the enthalpy of the system, we can get Gibbs free energy. And Helmholtz free energy is equal to H, defined as H plus U plus PV. Okay, Helmholtz free energy. Okay, so there is one derivation. If we derive, we can get the final equation delta G equal to delta H plus T into d by delta G by dt at constant pressure. This is called Gibbs-Helmholtz equation. This is the most important equation of thermodynamics, Gibbs-Helmholtz equation. Next thing is application of Gibbs-Helmholtz equation. So we can calculate heat change, enthalpy change of a reaction from delta G and its variation in temperature at constant temperature and pressure. The application is usually particularly in relation to reversible reaction in electrochemical cell, where delta G identify with the electrical work, that is minus NFE. We can calculate delta G reaction. We can calculate the change of delta G reaction for a reaction at temperature at a temperature other than 298 Kelvin. We can calculate the effect of temperature change on equilibrium constant by this Gibbs-Helmholtz equation. Next is what is standard free energy change. So free energy means H equal to H minus Ts. Now standard free energy means if we define the free energy at standard state, means at 1 atmosphere pressure, 298 Kelvin, then it will be called standard free energy change. To calculate standard free energy change, we have to calculate standard enthalpy change, temperature, and standard entropy change. Next one, free energy, relation between free energy and equilibrium constant. For spontaneous reaction, delta G should be less than 0. For equilibrium, delta G would be equal to 0. Now, standard free energy is defined as delta G 0. Now, there is a relation between standard free energy and equilibrium constant. That is, delta G 0 is equal to minus RT ln K. So, in that way, we can calculate equilibrium constant. So, ln K will be minus delta G 0 divided by RT. So, K equal to e to the power minus delta G 0 divided by RT. Right? So, in that way, we can calculate the equilibrium constant from Gibbs free energy. If equilibrium constant greater than 0, reaction will proceed. If equilibrium constant less than 1, reaction opposite reaction, reactant will form. If equilibrium constant is equal to 0, means reaction will be in equilibrium. Last one, there is some quantity that delta H, delta S minus T, delta S and J. Okay, so Gibbs free energy can calculate, means can predict spontaneity of a reaction. So if Gibbs free energy is 0, reaction will be non-spontaneous. If it is minus, then only reaction will be spontaneous. Now, there are some conditions, means at low temperature. At low temperature, T into delta S value, it will be, if delta S is negative, T into delta S value will be positive. So delta G can be positive or negative. If so, at low temperature, it will be spontaneous. At high temperature, it will be non-spontaneous. Similarly, if T delta S is negative, then also there is a chance of positive or negative. So at low temperature, non-spontaneous, high temperature, spontaneous. So from this table, we can predict whether some reaction will be spontaneous or not. Okay. So from this chapter, we have understood what is thermodynamics, what are the first law, second law, zeroth law thermodynamics, and what is the equation, the delta defined equation like delta G equal to A delta H minus T delta S, first law equation dq equal to du minus dq equal to du plus dw. Right? Defined equation we have understood. We have understood what is extensive properties, what is intensive properties. Right? Different things we have understood. Thank you all for listening. I hope this lecture will help you in your BTech chemistry. Thank you.